our first test. 2 pages, but it's very quick. But you can, of course. Ten questions, 10 minutes. It won't take more than 1 minute per question. It's just 1 out of 4.
얼마나 스키소서.
Okay, I'll give you the answer. So, the second kind of isometry, what it is an operation that changes left to right, changes handedness. So it keeps the hysteresis angle because it's an isometry, but it reverses the handedness. Conventional unit cell can be primitive or can be central, and is not always defined. If you take a triclinic, but there is no symmetry direction, so there is no conventional unit cell. The indices of a lattice direction can be integer or fractional, but they never have common factors, because you take the coordinates of the first lattice node along the direction after the origin, and that lattice node can be integer or can be fractional if it is in the center of a face or the center of the body of the cell. Meyre-Curie means that the point group of the pattern is a subgroup of the point group of the lattice. Can never be higher because the lattice is has the highest possible point group, but the pattern can be the same or can be lower. Combination of a two-fold rotation and an inversion. I told you that I will ask you 100 times this question, and of course it is a mirror that is perpendicular to the two-fold axis. Okay. How many lattice nodes contain a unit cell of type F? 4, because every face is a center. So 3 for each face and 1 for the corners. For a B-unique monoclinic setting, so the symmetry direction along B, which of the following equivalence is correct? Is F and I. Remember, C, A, F, and I are all equivalent. P and B are equivalent. So among these equivalents, the only one that was given here is a monoclinic F equal monoclinic I. Which of the following point groups belong to the cubic system? What is the feature of a cubic crystal? To have a 4 3-fold axis in the second position of the Hermann-Gunn symbol. So it was a 2, 3. An orthorhombic crystal has necessarily by 3 90 degrees angles. Alpha equal beta equal gamma. I don't put 90 degrees, but they are the same. The Miller indices of a lattice plane can have common factors, because if the unit cell is center, that could be 222, 200, etc. So these are the answers. Okay, it's just apart from you who get the credit for the lecture. For the others, is just to have an idea of what you have retained from yesterday's lecture. And we do the same every morning. It's just there is nothing. And if there is something that was not clear, at least you know that I have to ask again about it, go back to my slides, and so on. Okay. These are the exercise we have done yesterday, so in case you do that. You do the variance here, so in the evening I use question and answer corner in the dormitory. Yesterday the room on the left was taken, so I was in the room on the right, but you were probably too tired to come. But anyway, if you have further questions, we are going to do some exercise. This is always quite surprising. At the end, you are tired. What you just don't understand is that you are young, sitting and listening. I am old, standing and talking, and it's you who are tired. Anyway,
we have to use our brains to understand.
I use my brain to explain.
We are tired from the brain.
Okay. Let's go on. We finish with the point group. There are quite a number of interesting things to touch. And then we will move to space groups. Size symmetry groups, or called also stabilizers in mathematics, and the wide composition of point groups. If you understand this, then we have the same thing in space group, but of course, a bit more complex because we have translations. Okay. Let's consider P a crystallographic point group, which is therefore finite, because for crystallographic point group you have only operation of order 2, 3, 4, and 6. And take X a point in space. Its coordinates will be X, Y, Z. I consider the set of points that are obtained by applying the operation of the point group P to my point x. And so these will be x dash, x double dash, etc. These are equivalent because they are obtained by applying the operation of the point group. The set of points in space is called the orbit of x under the point group P. It's like the orbit of a planet around a star is simply turning, and this is the same idea. Now I take a subgroup S of P. Remember what is a subgroup? A set of operations taken from the original group, which still form a group under the same binary operation. How do I choose S? I take those operations of P which leave X invariant. So Sx equal X. This group always exists because at least the identity leaves the point invariant. So it could be just the identity or could be more. S is called the side symmetry group of X, also called the stabilizer. It stabilizes, it leaves it fixed, it doesn't move. Points whose side symmetry group S are conjugate subgroup of P belong to the same Wyckoff position. And that's something on which we come back again and again and again. This is the definition of Wyckoff position. The number of points that are obtained as Px is the multiplicity of the orbit. How many points belong to this orbit? Multiplicity. And is always equal to the ratio of the order of the two groups, which means the index of S in P. P is the order of vertical bar P is the order of P, vertical bar S is the order of S. You take the ratio, you have the index of S in P. And this is also the multiplicity of the orbit, number of points. Let's see an example so that things becomes clear. I have taken here, you have the slides on the participant page with the answers. Yesterday, we did, this is the third set, you see set number 3. The exercise that we have done already there. So there are a few corrections with respect to what I have sent you for types, etc. Please download the updated version. So here I consider two positions. One on the top, which has multiplicity 8, and one on the bottom, which is multiplicity
4.
How many points? 4. Can you read the point group from the stereographic projection? Here we have an axis of order 4. It's a 4 rotation axis. And here we have a tetragonal crystal. Here we have the symbol of 2 4 rotation axes. How many of them?
3.
1, 2, 3, 4. This is the sum. It's an axis. It's infinite. So what is the symbol of this point group? This and this are equivalent under the action of the 4 4 axis. This and this are equivalent under the action of 4 4 axis. So this is 4, 2, 2. Okay? These are the points that are obtained, stereographic pole, by acting this point group on any of the pole considered a starting point. So what are the Miller indices of these two projections? Here you have HKL, KH bar L. You remember, if you have a 90 degrees rotation or an operation about the diagonal, you exchange H and K, like exchanging the axis. And if it is y, it is south, so it's bar L. If it is black, it's north, so it's L. So you have a K bar HL, H bar KL bar, and so on. What is the order of the point group 422? How many operations in 422? It's isomorphic to 4mm.
8.
So 8, because 4 rotation for the 4, and then you have 4 2-fold rotations. So 8. Here we have 8 poles, and here we have 4 poles. Okay. The side symmetry group of this orbit contains only the identity. It's the only operation that leaves these points invariant. Or any of the other operations act on any point and moves it. This is called a general position. The size symmetry group is 1, contains only the identity, and the multiplicity then is equal to the order of the point group. Order 8, multiplicity 8, size symmetry group 1, general position. Here we have a special position. 1, 1, 0, 1, 1, 1 bar, 1 bar, 0, 1, 1 bar, 0, 1 bar, 1, 0. Now, the size symmetry group here are 2. These 2 points are fixed by the identity and by a rotation about 1, 1, 0. They are on the axis, so the axis does not change, does not move. But it moves this, exchange this and that. These 2 are fixed by the identity and the 2 for rotation about the other diagonal. So these 2 are different groups because one of the 2 operations is different. It's a rotation about this and a rotation about that. So it's not the same group. However, they are conjugate under P. Take any operation belonging to the point group P and do your conjugation. So if you act on the identity, well, you get only the identity, of course. But when you act on 2, 1, 1, 0, you get half of the time 1, 1, 0, and the other half 1, 1 bar 0. So this is a conjugation relation. This means that when you act on this group, you obtain always the identity, and half of the time this, half of the time that. Which means that these 2 groups are conjugate under the point group. No? Remember conjugation. This is a fundamental, very, very important notion, simple, but very, very important. What are the operations of What are the operations? 4, 4, 2, 4, 3, identity, 2, 1, 1, 0, 2, 1, 1, 0, 0, let's start. 1, 0, 1, 0, 2, 1, 1, 0, 2, 1, 1 bar 0. These are the operations of 4 to 2. And now I consider the group, subgroup 1, 2, 1, 1, 0. It's a subgroup of this. Okay? And now I want to act with P minus 1 for every P on 1, 2, 1, 1, 0. Minus 1. Conjugation, taking all the P operations. So I apply this to the identity, and I always get the identity. And I apply this to this. So let's see what happens. 1, 2, 1, 1, 0, 1, of course, is 2, 1, 1, 0, because the identity doesn't do anything. 4, 2, 1, 1, 0, 4, minus 1. What is this? Well, you can do the matrices, but we haven't done the matrices yet. So, but you can do it with a stereographic projection. What happens? You take a pole. Remember, you apply from the left. So this is 90 degrees negative. So you go here. Then you apply the 2110, which is here. So you go here.
One.
And then you apply force for rotation here. What is the relation between this and that? This one. So you get 2, 1, 1 bar 0. Simply apply the conjugation. If you do the same for the other operation, you obtain half of the time 2110 and half of the time 1 bar 0. Therefore, when you apply this conjugation to your group, you obtain half of the time 1 and 2110. 1 is always there. And half of the time 1 and 1 bar 0. Therefore, this side symmetry group and this side symmetry group are conjugate subgroup of 4 to 2. Remember, conjugation, you do the same thing somewhere else. This diagram, or that. If the side symmetry group of your position are conjugate under the group, then this position belongs to the same Wyckoff position. This is the definition of a Wyckoff position. We'll see this with the space groups, we'll see, and then we'll do also with matrices. And this is written in the way that you already know. Nothing along the first position, dot. Nothing along the second position, dot. 2 along the third position because it's the 2 for rotation. And you see here, you just take the symbol, but you don't specify which one. Because there is a 2 for rotation along the third symmetry direction. The third symmetry direction is this or that. So this is a synthetic symbol. And the multiplicity is 4 poles. What is the order of a point group 2? Operations. 8 divided by 2 is 4. And indeed, the multiplicity of the Wyckoff position is 4. It's always in the same way, very easy. This is called a special position. When the side symmetry group is a supergroup of the identity, there is something more than the identity, it's a special position. And the multiplicity is the order of P divided by A, the order of S, or the index of S in P. Clear? We will find this in space groups by the translation, so there is not only the orientation, will be also the position of your symmetry elements. Okay, subgroups versus space groups, supergroups. To remove symmetry operation is always easier than to add. The number of possibilities is lower. Consider a group, a subgroup, the index is the ratio of the two orders. When you go from G to H, you have a number of possibilities. But when you start from these subgroups, you can go back to G, but you can have a G dash, you can have a G double dash, because when you increase, the number of possibilities is large. Consider AVA 4 to 2. And I want a subgroup of index 2 which is orthorhombic. So we will type 2 to 2. I get two possibilities. 2 to 2 dot or 2 dot to 2, depending on whether I get these two or these two. And now I do the opposite. I go up to a tetragonal supergroup of index 2. If I start from this, what should I get? I can get that one, but I can also get this one or that one, because the 4 for rotation could be along any of the three twofold rotation axes. And of course, from here, I can also get the same. So you see, from here to here, I get two possibilities, but from here to here, I get not one, but three. And this is precisely the idea of phase transition, when you have something that goes into a domain, and then you increase, but you can get a number of possibilities, depending on which of the original axis is promoted to a higher order axis. Okay. Bravais-Miller indices. We have played yesterday with Miller indices, but when you have an hexagonal coordinate system, things may become a bit more complex to see, and we have a trick to make it easier to read, easier to interpret. We add an additional axis in the AB plane, which is not independent, of course, because in a plane you have two independent directions. All other direction is a linear combination of the first two, but it can be useful. So if you consider a hexagonal coordinate system, you have the interaction angle of 120 degrees. You remember we have seen yesterday, A equal B, C, alpha and beta gamma 90 degrees, gamma 120 degrees. Now, from A to B, I have 120 degrees, but from B to A, I have 240 degrees. Obvious. 360 minus. And now, if I add an additional axis called, this time I will call them A1, A2, A3, the drawing looks more symmetric, because every 120 degrees I have an axis. But this means that I have 4 axes in a 3-dimensional space. Clearly, one is not necessary, but it's useful. So I move from ABC to A1, A2, A3C. And, of course, I will have 4 indices as well. Because if I have 3 axes, I have 4 axes, I have 4 indices. Now, these are called Miller indices, and these are called the Bravais-Miller indices. What is the linear combination of A1 and A2 that gives you A3? How you can express A3 is a linear combination of A1 and A2? Sum of vectors. So, what is A3?
A1 plus AB and
Negative.
no,
Minus A1 minus A2. Okay. And then I, exactly the same, minus H minus K. Linear combination. Why it is useful? Let's see. Consider this stereographic projection of a hexagonal pyramid. What are the Miller indices? And what are the Miller indices? I start from, I think I started from this one. We start from HKL always, and then we use the information that we know. This is a pole of a face that is parallel to A2. It is inclined to a certain degree, but it is parallel to A2. A2 is there, the face. All faces that are on this zone are parallel to A2. If it is parallel, they are not intersects, so the index is 0. So we have a K equals 0. So I move from HKIL to H0IL. But I know the H plus K is equal minus I, or I equal minus H minus L, minus K. So I use these equivalents. Minus H minus K, K is 0. So I obtain H0, H bar N. Then I do the same for the others, and I have simply a permutation. This one is parallel to A1. It has a positive intercept on A2, a negative intercept on A3, so it's A0, H bar N. This one, the face, is parallel to A3, so I is 0, has the same intercept on A1 negative and on A2 positive, H bar, H0, L. And the others, well, they are just 190 degrees, so this one you change the sign of the first three. This one is the same as this, change the sign. This one is the same as this, change the sign. Now, if I express this with Miller indices instead of Bravais-Miller indices, I simply forget the third one. And so I get this. H0L, 0HL, H bar, HL. So you see there are, in 4 cases there is a 0, and in 2 other cases there is no 0. It looks like a form of 4 faces, another form of 2 faces, if you just look at the indices. Whereas if you use Bravais-Miller indices, you see there is always H bar, 0. It's just a permutation. So the Bravais-Miller indices give you a clear idea that this is one form. The advantage of using four axis. Same, but this time parallel to C as well. What I have? This is parallel to C, so L equals 0. And this is parallel to A2, so K equals 0. So what happens? I go from HKIL to H0, I0. Then I know that I is minus H minus 0, which means that I have H0, H bar 0. I simplify by H, because it's a common factor. If it is hexagonal, you would say it's primitive. So I have 1, 0, minus 1, 0. This one will be 0 plus minus. This will be minus plus 0. And the others are simply with the minus. And so, what do you get? Let's look at the Miller indices. 1, 0, 0, 0, 1, 0, 1 bar, 1, 0. It doesn't look very much symmetric. While if you use the Bravais-Miller indices, these are much more symmetric. Another case. Let's look at this on another zone. What happens? This has the same intercept on A1 and A2. The pole is on the bisector, so the intercept on A1 and 2 is the same, which means that H equal K, or K equal H. So I move from HKIL to HHIL. But now I add information, I equal minus H minus K. K could be equal to H, I have minus H minus H. Which means that I have HH bar to HL. With this bar 2, you can see also with a simple geometry. The face is oriented in this way, but then inclined, okay, but with respect to A1 and A2 is inclined in this way. This is an isosceles triangle, and half of it is a rectangular triangle. Here you have 60 degrees, so this is 120 degrees, and this is 60 degrees. This is 90, this is 30. So this one, what is the sine of 30 degrees, which is 1/2. And 1 over 1/2 is 2. Precisely our 2. Then we are in the negative part of A3, and so it is minus 3. You can see with a simple trigonometry. This one is the positive intersection of A2, negative of A1, and negative of A3. So it is H bar 2H, H bar L. This one, negative of A2, 1/2, positive of A3, positive of A1, 2 bar H, 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 L. And the others, you just switch the signs, because 180 degrees behind. If now you use the Miller indices instead of Bravais-Miller, you see that sometimes you have a factor of 2, and sometimes you don't have it. So it doesn't look very much symmetric. Whereas the Bravais-Miller indices immediately hints that this is a hexagonal form. And if we take the form whose faces are parallel to L, which means we move from an hexagonal pyramid to an hexagonal prism. What we have also C parallel to C, so L equals 0. And with again the same intersection on K and H, so we move from HKIL to HHI0. I is minus H minus H, HH bar to H0 divided by H, and you get 1, 1 to bar 0. And then in permutation, this is positive of B half and negative of A1 and A3, negative of A1 half, positive of A3, positive of A2, and the rest is simply a change of sign because it's 180 degrees from the others. And if you do the indexing with the Miller indices, you see that sometimes you have 1, sometimes you have 2. Doesn't look very much symmetric. The advantage of using the Bravais-Miller indices. So if you have an hexagonal coordinate system, it's always preferable to use this additional axis. It's not independent, but you see that the symmetry is much clearer. Okay. We haven't seen 3 of M. We have seen 2 of M, 4 of M, 6 of M, but not 3 of M. Why don't we see 3 of M? 3 over M is a trigonal bipyramid. 3 for rotation, reflection, and you have so pyramid by pyramid. In morphology, a trigonal bipyramid exists. You will see it. Let's do the stereographic projection. 120 degrees, then you go down because you have a mirror. This is never expressed as 3 over M. This is expressed as a 6 bar. 60 degrees inversion, 60 degrees inversion, 60 degrees inversion, and so on. So we have 2 possibilities. But we never use this one. We only use this one. Why? Pretty simple. In hexagonal crystal system, you have 2 possible lattices. Hexagonal and 3 bar, 6 bar, M perpendicular to C, all act on this lattice. Act means live invariant. If the lattice is rhombohedral, only 3 and 3 bar act on it. 6 bar, M, we have seen yesterday, is not compatible. Now, if you write 3 over M, you have 3, which means trigonal system. You can act on 2 lattices. If you write M, but you see that M cannot act on here, act only on this. And so this means that here you have HP. Only hexagonal system. Except it is only on. So this is clearly a contradiction because the numerator means trigonal system and the denominator means hexagonal system. What is the lattice that is common? HP. And so we have to express this in a way that indicates the crystal system is hexagonal. And this is why you use a 6 bar. Because when you see this hexagonal system, only 1 type of lattice. If you see 3 is trigonal, 2 types of lattices. But M is not compatible with the rhomboidal lattice. The symbol of the stereographic projection, the symmetry element of the stereographic projection represented here. You have 6 bar. 6 bar twice is 3. And 6 bar 3 times is M. 160 degrees 3 times is 180. And then you add the inversion. 3 times inversion is 1 time inversion. But what is 2 bar? It's M. So you see, we have a 6 bar which contains 3, which contains M. So the mirror, that is perfectly visible in the morphology, does not show up in the symbol because if you write as 3 over m, you have this contradiction. You say, is a trigonal crystal? No, it's an hexagonal crystal. That's why you never see 3 over m. Just a matter of a warning. Leonard Weber long ago had a very bad idea of using 4 indices also for the directions. If you use in electron microscopy, this bad habit is still alive, unfortunately. Weber indices are simply the Bravais-Miller indices of the plane to which a direction is perpendicular. So instead of giving the direction indices, Weber indices give the direction of the plane to which the direction is perpendicular. But if it is not a symmetry direction, there is no direction perpendicular to this one. So the Weber indices, well, this comes also from the fact that in electron microscopy, when you orient your crystal, you have to choose a zone which is an important zone, otherwise the diffraction pattern you see almost nothing. In the electron beam gives a diffraction pattern that is at very low angles. So if you take a general direction, you see almost nothing. You have to take an important zone axis, which means that is for the hexagonal crystal is a perpendicular to one symmetry plane. But this is just an experimental limitation. Okay, if you take any plane of an hexagonal crystal, you don't necessarily have a direction that is perpendicular to it. So if you give the direction of the plane, you end up with a direction that is not rational. So there is absolutely no need to use this trick. So I recommend to never use Weber indices because they are a mixed. For a general case of a plane of a direction that is not perpendicular to a plane, this actually corresponds to a direction in reciprocal space. We'll come to this. So it's sort of mix of direct and reciprocal space. So Bravais-Miller indices are absolutely useful in the case of a hexagonal ordinate system. Weber indices, just forget that. Use the normal direction indices. That was a very bad idea, but unfortunately still used today in electron microscopy field. Yes?
I have questions. Why usually when people report crystal structure, at least in physics, they only use Miller indices
Yes.
rather than Bravais?
Because physicists do not know crystallography. As simple as that.
So, but in the other field, it's often used then.
Yes. Yes. We always use Bravais-Miller indices. Unfortunately, there are many mistakes in physics when you come to solid state. Not in the band theory, of course, but in the description of crystal structure. It's typical of physicists, they do not understand the difference between a lattice structure, what I meant yesterday. Because quite often solid state physics have a high symmetry, so you have cubic, hexagonal, already orthorhombic can pose some problems. When you go to monoclinic, physicists are hopeless. With not everybody, of course, there are physicists who know very well crystallography, but in general, it's a shock. If you take the Kittel, the crystallography description of Kittel is a nightmare. And a very short chapter that they consider, okay, they do more crystal chemistry, sphere packing, etc., and then no time to learn this stuff. They consider that they are above this. But when you consider yourself above something, that is a trap. Bravais-Miller indices are definitely useful. But Weber indices instead, forget. I mentioned because you see them in the literature, and if you read some electron diffraction, electron microscopy paper, then unfortunately you say, then you lose. But what is the direction? Does it coincide at all with what I've learned? Yes, because they use this strange system that should never be introduced. Okay, some application to crystal physics. It's just a quick introduction. There is, of course, much more than one could do, but we are limited in time, so just some ideas. Curie laws. Curie's law, for that we have introduced the Curie groups. Curie groups are groups that contain at least one infinite axis of or infinite order, because they describe the symmetry of some physical phenomenon. There are 7 Curie groups divided in two systems, a cylindrical system and a spherical system. Here you have a cylindrical system when you have one axis of infinite order, a spherical when you have, of course, more. Now, these are 5 Curie groups with one axis of infinite order. Could be just the axis infinite, could correspond to a chiral object because it's only first kind operation. Can be represented as a polar vector spinning or a cone spinning. Here you have 2 possible directions. Infinite over m or bar infinite corresponds to a axial vector, direction and the sense of rotation about it. Or can also be 2 cones pointing one toward the others and spinning. Infinite 2 is like a polar vector, axial vector with 2 parts rotating one on the opposite side of the other, or 2 cones that are spinning in the opposite direction. A static polar vector infinite m, infinite number of planes that contain this infinite, or the axis of infinite order. Infinite over mm or infinite over m, 2 over m is a double cone. And then you have a spinning sphere or static sphere. This is also isomorphic to the orthogonal group and to the special orthogonal group. The orthogonal group is a group that contains all linear isometries. No translation, but all the isometries without translation. And the special orthogonal group is the group that contains all the isometry of first kind, without translations. So these are the 7 Curie groups. Okay. When you apply a field to a crystal, you observe an effect. The crystal reacts to this applied field. So let's consider K the point group of the crystal, K crystal. F the point group of the field that you apply to the crystal. And G is the point group of the resulting phenomenon, the phenomenon that you observe in your crystal. Necessary but not sufficient condition for the phenomenon to occur is that the phenomenon has a point group which is equal or higher than the intersection of the symmetry of the point group of the crystal around the field. In other words, yes?
It means the field is some kind of Curie group? Or?
No. You can, what is the symmetry of an electric field? The point group of an electric field. How do you represent an electric field? As a?
Maxwell. Using Maxwell equation.
Yeah, no, but not simple, just the symmetry.
Symmetry.
How do you represent when you draw an electric field? It's a vector. It's a polar vector. Okay? Vector like. So, an electric field like this. So its point group is infinite. A magnetic field is more like an axial vector. A compression it's not a couple, it's in the same direction, so it's like this. Or compression or expansion. This is a mechanical field, okay? Of course, in one sense or the other sense, the symmetry is the same. So this is the action that you do on the field, on the crystal. And we have the Neumann principle that says that actually the crystal is its symmetry must be compatible with all physical phenomena that you can observe with that crystal, which means that my point group must be a subgroup of the phenomenon that you want to observe. Translated to Curie laws, this means that it's the dissymmetry, the lack of symmetry, that allows the phenomenon to be observed. In other words, the crystal should not be any symmetry operation that is incompatible with the phenomenon that you want to observe. Let's go with some examples. 2. Pyroelectric effect. The pyroelectric effect is the combination of heating up and electric field. Pyros in Greek is the fire. So the idea is that you warm up your crystal isotropically. There is no gradient, it's simply change of temperature. And you may observe, in some cases, the development of an electric field. Is a temporary phenomenon, okay? Then everything goes back. If you have a permanent field, then is a ferroelectric. If you have a temporary electric field, then what you get is called the pyroelectric effect. Okay. The field is a static sphere. It's total symmetry, because the temperature, what is the temperature? It's a scalar. It's not a gradient of temperature with a vector. It's just a scalar. A temperature is a number, and is a chiral. So this means that the intersection of the crystal point group with the field point group is just the symmetry, is a point group of the crystal. Because when you get the orthogonal group intersection with anything else, only this anything else remains. Because the sphere is totally symmetric. So, what is the point group of an electric field? It's a vector, polar vector. So it is infinitary. When you draw a vector, a polar vector like this, you can do any rotation here, because it's a vector just limited in the rotation. And of course, any plane that contains this vector is a symmetry plane for the vector itself. However, there is no mirror perpendicular to it. There is no 2-4 rotation perpendicular to it. There is no inversion, because up and down would kill the effect. Now, if the crystal contains any operation that reverses your vector, then the sum of the two is 0. So, the crystal must not contain any operation like a 2-4 rotation perpendicular to the principal direction, or an inversion center, or a plane, because any operation that switches the electric field from one sense to its opposite would kill the electric field. Two vectors that are identical by opposite direction give a 0 vector. So, if you consider the 32 types of point group that we have seen yesterday, we have derived a number of them, but then you have my tree with all the 32 types. What are these groups? 1 bar and 1, 2, M and 2 over M, triclinic, monoclinic. 2, 2, 2, m, m, 2, 2 over m, 2 over m, 2 over m, orthorhombic. 4, 4 bar, 4, 2, 2, 4 mm, 4 bar to m or 4 bar m2, which is simply 45 degrees rotation, 4 over m, 1, 2, 3, 4, 5, 6, and 4 over m, 2 over m, 2 over m. Trigonal, 3, 3 bar, 3, 2, 3 m, 3 bar, 2 over m. Hexagonal, 6, 6 bar, 6 over m, 6, 2, 2, 6 mm, 6 bar to m, 6 over m, 2 over m, 2 over m. Cubic, 2, 3, 4, 3, 2, 4 bar, 3 m, m, 3 bar, 4 over m, 2, 3 bar, 2 over m. 5 cubic roots. And we simply have to get rid of all groups that are incompatible with the electric field, which means our group, they contain at least one operation that reverses the direction of the field. So first of all the centrosymmetric groups must go. Centrosymmetric, 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 centrosymmetric. Next, all the groups that have a rotation axis perpendicular to another rotation axis, because this will switch north-south, up and down. So 2, 2, 2. 2, 2, 2, let's do a very simple reasoning. Whatever is the direction of your field, what happens? If you have a group of point group type 2, 2, 2. Suppose you have an electric field that develops in a certain direction. This means coming out north, okay? When you act, for example, with these two fold axes, you must have the same field along this, which means that you have vector sum, the resultant field along this direction coming out. But then you have a two-fold axis there, and so you have the same field going down, and so it is oriented along this axis. And then you act with these two-fold axes. You have another vector here. You make the vector sum is 0. So whatever direction you consider for your possible electric field, it is annihilated by the crystal symmetry. So when you have a two-fold rotation axis perpendicular to something else, this is not compatible with the development of a crystal field. And then we are still with the inversion point. This is not an inversion axis, but nevertheless, there is a component of the operation that make inversion. Or if you want, you have also, you see two-fold perpendicular to another two-fold. So this is gone, inversion point, and inversion point. So we have left with 1, 2, m, mm2, 4, 4 mm, 3, 3m, 6, 6 mm, and these are the 10 pyroelectric or polar groups. And if you look at the list here, you simply see that there is one axis alone, or one axis with a mirror that contains this axis, but nothing perpendicular. So you have identity, axis of order 1, or one mirror. 2 for rotation axis, or 2 for rotation axis with 2 mirrors. 3-fold, or 3-fold with 3 mirrors. 4-fold, or 4-fold with 4 mirrors. 4 mm, sorry, there is an mm missing here. 6 or 6 mm. These are the 10 pyroelectric groups. So in case of a paraelectric effect, it's very simple. You look at the point group of your crystal and you say yes or no, I can or I cannot have a crystal field, electric field development. Piezoelectric effect. Piezoelectric is a combination of a compression or expansion with a mechanical field with an electric field. And there is the direct and inverse effect. Depending on whether you apply electric field and you observe a deformation of your crystal, well, you observe in diffraction, of course, is very small. Or when you apply a field, a compression, and you observe an electric field. Well, the necessary condition is that the intersection of the crystal field and the compression should be a subgroup of the group of the electric field. So what is a compression? Two vectors that point one towards the other. Expansion will be, of course, the same, but the other different sense. So what is the point group of this double vector? Well, axis of order infinite, any plane that contains, but you can also reverse. So it's also 2 over m. And so now we have to find the intersection of the two and see whether the result is compatible with the development of electric field or not. And so let's do it with a simple example. I take, well, the classical case of quartz. If you have some old style watch like me, then you have some cut from quartz that resonates via the battery inside. This is gives as a result a small deformation that gives the period actually of your watch. So this is a crystal model of crystal of quartz. Its point group is 3 to 1. And I have to see whether I can get something that is compatible with the development electric field. Of course, I know there is a possibility because quartz is used in watches, but I have to find on what direction. Let's see. So the field is infinite over m to over m because it's a compression, it's a mechanical field. The crystal is 3 to 1. This is a trigonal crystal which has 0, 0, 1 for the first direction, 1, 0, 0 for the second, and 1, 1 bar 0 for the third. There is nothing along the third. So, the stereographic projection of the symmetry of elements of quartz is simply 3, 2, and nothing along the third. This is fixed. And then the compression, but I can do it in many possible ways. Let's consider this compression, and this. So along the c-axis, along the A1, A2, or 3, or along the bisectors. Sorry. And so this is K, this is F, this is K intersection F. How do I represent the compression? Well, when it is along C, I don't see them. So I write a sort this way. You see, it's like an arrow that goes down. So it's sort of going down along the direction of the arrow. So I have to look for the directions that have symmetry operation in the crystal. All the others have nothing, so of course intersection will be 1. So how many directions do I have? 0, 0, 1, 1, 0, 0, 0, 1, 0, and 1, 1, 0. For the crystal, what do I have? 3, 2, 2, 2. The crystal is fixed. For the field, it depends on its orientation. Okay. For the 0, 0, 1 direction of the crystal, what do I have in my compression field? If I do the compression in this direction, what is the symmetry along this direction? Remember, the field has this point group. So what are the operations along the C direction of the crystal? Considering that I am doing the compression in this way. The direction of compression is a rotation of order infinite. And of course, I have also y. What about A1 of the crystal? What do I have in the field? Infinite of m is here, and any direction that is perpendicular to the axis of order infinite is 2 of m. Compression, and then you can do a rotation along any direction that is perpendicular to my compression. So here I have 2 of m. This again is perpendicular to the c-axis, so it's 2 of m. Here again I have 2 of m. So in the intersection, sorry, K, F, K intersection, 3 and infinite over m, what do I have in common? Taking intersection means leaving what it is common. Between 3 and infinite.
3.
3. And of course there is no m. Between 2 and 2 over m.
2 over m.
Of course, 3 times the same. So if you compress your quartz along the c-axis, the symmetry of the point group of the quartz will not change. But 3, 2, 2, 3 to 1, sorry, is it a subgroup of infinite over m? Infinite m, sorry. Infinite m is the electric field, okay? I want to observe an electric field. The symmetry of an electric field, which is a polar vector, is infinite m. Is 3, 2, 1 a subgroup of infinite m? Subgroup means it must have less operation than this, but nothing more.
Mm-hmm.
No, because 3 is lower than infinite, but I have 2 for rotation axes that do not appear here.
Mm-hmm.
So this is not a subgroup,
Mm-hmm.
which means that doesn't matter how strong you compress your quartz crystal, you will never observe an electric field. You can break the crystal, you won't observe an electric field. So it's not along this direction that you can apply your compression if you want to observe an electric field. Okay, wrong answer. Let's try along another direction. For example, along A1. Well, let's put it here. Easier. If I put the compression along A1, what's going to change? What do I have along 001 for my compression field?
2 over
Yes, 2 over n. What do I have along the 100?
infinite over
Infinite over n. What do I have for A2?
2 over
No. It is diagonal with respect to the field, the compression. So what do I have? Diagonal, what do I have? Compression is here, in a direction that is diagonal, not parallel, not perpendicular. Nothing, one. What about 110?
2
It's another
over 1
nothing. So, between 3 and 2 over m, what do I have in common? Identity. Between 2 and infinite over m, 2 and 1, of course 1, 2 and 1. This means that if you exert a compression perpendicular to a face of your hexagonal prism of quartz, the point group of quartz is reduced to 2. It's no longer 3 to 1. But 2 is a pyrroelectric group. 2 is clearly a subgroup of infinite M. Therefore, if you exert a compression along this direction, the electric field is developed along the same direction as the compression. 100. I cannot know if the electric field is strong enough to be useful, concrete use or not. This is just a drawing, okay? If you want to know the strength of the field, you have to do a tensor calculation, of course. But at least this tells you yes or not. How much? I don't know. How strong? I don't know. Okay, the drawing, I cannot go up to there. But at least, another possibility. What about compressing along the edges? So I do this. Same reasoning. What do I have for the 001 of the crystal? If the compression is here. 2 over m. What do I have for the 100 direction?
1
1. What do I have for the A2 direction? 2 over m. What do I have for the 110? 1. Intersection 3 and 2 over m. 1. 2 and 1. 1. 2 and 2 over m. 2. 2 and 1. 1. Again, I have 2. But now the direction along which the electric field can develop is perpendicular to the direction of compression. You see, here is the two-fold axis that remains. Again, I can have a electric field, but now instead of being along the compression, is along the direction that is perpendicular to the compression. Pretty simple, isn't it? Once you get the idea. There are a lot of other phenomena that one can study in the same way. And this is just qualitative, it's not quantitative. I cannot know the strength of the field. For that, I have to do some calculation. True. But you see the power of the method. We just one row. There is much more than one could do with about the crystal physics, but just a short one. Always something out of the things. Okay. So I think we have done enough about the point groups. Well, one could more, of course, but we have to go to something that is more related to experimental work. Introduction to space group. Remember this slide because now it becomes even more important. A geometric element is the subspace that is left invariant by the operation. A symmetry operation is an isometry that moves your structure from a configuration to another configuration which is equivalent. So you cannot differentiate them unless you see the movement itself. The element set is the set of operations that have the geometric element in common. And the symmetry element is the combination of the two element set plus geometric element. How do we call the symmetry element? We give the name depending on the defining operation. The operation that defines that gives the name. For point group was trivial. For space group, you see, it's one has to be a bit more careful. Okay, we want to see what happens when we add translations to our operation that we already see. So rotations, reflections, inversions. And we do this first of all in two-dimensional space because, of course, it's easier to understand. And now, when you add the translation to your glide reflection in two-dimensional space, to your reflection in dimensional space, you get what is called the glide line. And the operation is a glide reflection. So, now these circles are atoms. Here I have a reflection line, two equivalent atoms. And then we add the translation. From here to here, you have a period, of course. To fix idea, let's say that this is the 0-1 direction. Could be 1-0, could be anything else, doesn't matter. This is your period P, and this is another possibility. You will reflect and move along, reflect and move along, so the period now is this one. Of course, this is a half a period. Okay, let's put some color so that I can study the relation between a pair of atoms starting from the white one. White to yellow, it's a glide with the 0 component. This is a reflection, as you already know, so it's simply M. White to black is a translation. One period along B. White to red is a combination of reflection and translation. So this is a glide G01. White to blue, translation of two periods. White to purple, glide, reflection plus translation of two periods. White to orange, translation of two periods. White to cyan, reflection and translation of two periods. So a glide 0-2. And so on. Of course, you can go in the negative direction, okay? So what do you see here? The defining operation, the operation that gives the name to the symmetry element, is the one that has the shortest glide component. In this case, the shortest is 0. So this is a reflection. Therefore, we call it a mirror line. But it does not contain only, does not act only as mirror line. It contains an infinite number, infinite many glider reflections. But the shortest one is a pure reflection. Therefore, we call it a mirror line. It doesn't mean that it acts only as a reflection, as operation. It's an infinite many glides. But the one that gives the name to the defining operation is a reflection. So this is a mirror line. Next, white to orange. We have a reflection followed by the translation of half a period. So this is G01 half. White to blue is a translation of one period. Sometimes the animation is slow, I don't know why. White to cyan is a reflection for the translation by 3 half period. And so on. Okay? You go up, you go down. What is the operation which has the shortest glide component? This one. And is itself a glider. It's not just a pure reflection. Therefore, the defining operation is a glide reflection. And the symmetry element is called a glide line. You see the difference? Mirror line, glide line. Both act with an infinitely many glide reflection. It's just the one that gives the name, the defining operation, that is different. Here you have no glide component, so is a mirror line. Here you have a glide component, so is a glide line, a glide line. Do you get the idea? Over into D, so let's apply it to 3D. Screw axis, rotation plus translation. Same drawing, but now instead of having a reflection, we have a out of plane rotation, 180 degrees. Same reasoning, so it's pretty much similar. This is a rotation of 280 degrees followed by 0 translation. So it is a 2, 0, which is shortened to 2. The symbol is P over N. It is NP with the translation component, screw component of P over N. So this is NP with the translation P over N. P over N. White to black is a translation. I'm taking this as C direction, but could be AB, could be A, could be 110, doesn't matter. White to red. What will be the symbol of this? We have a rotation followed by a full period translation. So this will be written as P over N must be 1 because it's a full period. But N is rotation is 2, which means that P is 2. So the symbol is 2, 2, exactly. White to blue is a translation of 2 period. White to purple is rotation followed by translation of 2 periods. The symbol will be 2, 4. White to red is a 3 period translation. White to cyan, the symbol is
2, 6.
and so on. You can have 2 minus 2, 2 minus 4, etc. Among all these infinitely many operations, the one that has the shortest translational component is 0, 2. So this is the defining operation. The operation that gives the name to the symmetry element. So this defining operation is a twofold rotation. which means that the symmetry element is called a rotation axis. It does not mean that it does not act as a screw axis, because it contains an infinite number of screw rotations. But the one that gives the name, the defining operation, is a pure rotation. That's why we call it a rotation axis. Next, white to red is a two-fold rotation followed by half a period translation. The symbol will be
2, 1.
2, 1. White to blue. Always to slow the animation at this point, I don't know why. This is a translation of one period. White to charm.
2, 3.
Hopefully. Is a translation followed by 1.5 period. So this will be
3.
2, 3. And so on. You have to find to -1, to -3, and so on. Among all these operations, that one and one that has a shortest translational component is to 1, shortest positive. So this is the defining operation, which is itself a screw rotation. Therefore, we call this axis a screw axis. You see the difference? Both act with infinitely many screw rotations. Among these, the one that has a shortest component is 0 or non-zero. So the defining operation is a pure rotation or is a screw rotation. That's why we call it a rotation axis or a screw axis. Is it clear? Okay. Next we analyze the different screw axes and then we move to glide planes. Perhaps a nice moment to increase the caffeine level. Okay, see you in 15 minutes. I see you are filming.
Oh,
It's okay, but keep it for you. Okay,
of course.
don't put on YouTube, etc.
Okay. Yeah.
I think 15 minutes.
Yeah.
Of course. That's good.